Hello everybody. So I hope you are keeping really well because today you should be in the highest of your spirits to attend this lecture. We have gathered today basically to polish all the concepts that we have learnt about complex numbers and quadratic equations. Today we will be basically testing our knowledge because we will be applying all the conceptual knowledge in our questions which we would be addressing today, which basically concern your JEE main pattern questions. Well, if I segregate the entire mathematics syllabus into 4 units that accounts for algebra, coordinate geometry, calculus and trigonometry, the highest weightage is of algebra unit. And inside it lies this particular chapter, which is complex numbers and quadratic equations, which out of 120 marks accounts for 7 full marks. Yes, 35 marks weightage goes to the algebra section on an average, and out of that 7 marks goes to the chapter complex numbers and quadratic equations. If I go by the analysis, in 2014, there were 3 questions directly asked from this particular chapter in JEE Main. In 2015, 2 questions, 16, 2 questions, 17, again 2 questions. And so if you observe, at least 2 questions from this chapter are always repeatedly asked in JEE Main, and 3 to 4 questions in fact are posed in JEE Advanced from this chapter. Okay? That is why I would again suggest you to be very conceptually strong regarding this chapter and not go by a lot of tricks which basically are just there to confuse you, get applied only on certain questions and not all the questions. So it is very crucial for you to understand all the concepts, clear all the concepts about this chapter and then get ahead to solve certain questions. So let us do certain questions which are based upon the JEE main pattern, which are going to help us polish our concepts very nicely. Let's look at the first question. It is talking about roots of an equation. The moment you read the trigger word from the question, just the entire concept about roots of a quadratic equation should be there in your mind. Entire picture should be there in your mind. Okay? Let's read further. Let both roots of this particular quadratic equation be greater than 3. That's the main major trigger word. Both roots of this quadratic equation are greater than 3. Now the thing which is right now popping inside my brain is that I have learned something about what are the conditions when 2 roots of a quadratic equation are greater than k. Isn't it? Let's polish that concept and then get back to the question in order to tackle it. Well, if ax square plus bx plus c equals 0, where a is non-zero, has 2 roots, alpha and beta, such that alpha and beta both are greater than k. K is any number on the real line. So, if alpha and beta are the 2 roots of this quadratic equation such that both are greater than k, then the condition are, what are the conditions? Well, there are 3 conditions which should be satisfied for this quadratic equation to have both its roots to be greater than k. Fine. What are the conditions? First thing is that the discriminant should be non-negative. We know that. Secondly, now why discriminant should be non-negative? Because either both the roots are real, or both real and unequal, or both the roots are real and equal. But if discriminant is less than 0, that means there are no 2 real roots. And that is not the case which is happening over here. So discriminant can either be positive or discriminant can be equal to 0 as well. Next condition is a into f of k should be positive, where a standing here is the coefficient of x square, which is non-zero, and f of k is the value of fx at k, where I am saying my fx is nothing but the quadratic polynomial associated with this quadratic equation. Fine. And the third condition was what? It was that the abscissa of the vertex of the parabola being represented by this particular quadratic polynomial should be what? Greater than k. The abscissa of the vertex is this only, right? Minus b upon 2a comma minus d upon 4a are the coordinates of the vertex, out of which the x coordinate is this. This should be strictly greater than k. Only and only when these three conditions simultaneously are getting satisfied can I say that the two roots alpha and beta of this quadratic equation are greater than k. Fine. So these are the three conditions which should be satisfied regarding this quadratic equation. In our question, we are given this type of a quadratic equation. Let's copy that down. It is x square minus 6ax plus 2 minus 2a plus 9a square. This is my fx, and I have considered fx equals 0. Fine. This is my quadratic equation. What is my a? A is 1 over here. If I compare it to the general quadratic equation ax square plus bx plus c, this is 1x square. Fine. B is what? Minus 6a. And what is my c? That's the constant term. 2 minus 2a plus 9a square. Fine. If this quadratic equation has two roots strictly greater than 3, so let the two roots be alpha and beta. So either these two roots are equal to each other, right, or they are unequal to each other. In any case, one thing is evident, because a is strictly positive. A is strictly positive. The parabola which will be represented by this particular polynomial will be opening upwards, right? You will have your parabola opening upwards. So if a is positive and discriminant is also positive, then what is going to happen? The parabola is basically going to open upwards. Fine. Intersecting the x-axis at two distinct points, which happen to be your roots alpha and beta. Or you can have a scenario in which a is positive but discriminant is 0. Again the parabola opens upwards, but this time alpha is equal to beta, right? This is nothing but ax square plus bx plus c, and this is also ax square plus bx plus c, where a is 1, b is minus 6a, and c is your 2 minus 2a plus 9a square. If both the roots of this particular quadratic polynomial which is given to me, fx, are greater than 3, in that case, I know what are the three conditions which govern this particular concept. Well, if both the roots are strictly greater than 3, definitely 3 is over here, they both are greater than 3, or it won't be such a polynomial because of such a graph, because over here alpha is coming out to be less than 3. Alpha is coming out on the negative real line. So instead of this, you can have, if discriminant is strictly positive, you are going to have something like this type of a polynomial. So this will be your alpha, this will be your beta, somewhere here is your 3 lying. This is ax square plus bx plus c when a is positive and d is also positive. So if such is the case, definitely the first condition which should be satisfied by my quadratic polynomial is that its discriminant should be non-negative. So that's the first condition, that discriminant should be non-negative, which means b square minus 4ac should be non-negative. That's the formula of discriminant. Now b square, what is b? b is minus 6a, minus 6a whole square, that means 36a square minus 4 into a into c. a is 1 and c is 2 minus 2a plus 9a square. This has to be non-negative, which implies 36a square minus 8 plus 8a minus 36a square. Isn't it? This is minus 8, then you have plus 8a minus 36a square. This 36a square, this 36a square, they get cancelled. You are left with 8a minus 8 is non-negative, which implies 8. a minus 1 is non-negative. So for 8 into something to be non-negative, definitely that something also has to be non-negative, right? Because 8 is already positive. So 8 into anything negative will give you negative, but the answer is non-negative. So 8 into something is giving you non-negative, means this thing has to be non-negative, which implies a minus 1 has to be non-negative, or a has to be greater than or equal to 1. So the first condition which is going to permit this particular quadratic equation to have both its roots to be greater than 3 is that, first of all, a has to be greater than or equal to 1. And there is something more which should be holding. What is that something more which should be holding? That will be given by the second very condition, which is a into f of k has to be greater than 0. Fine. So if both the roots are greater than 3, definitely a into f of k has to be, it will be greater than 0. What is a? A was 1. A was 1. So f of k, where k is 3, has to be greater than 0. What is f of 3? So if f of x is x square minus 6ax plus 2 minus 2a plus 9a square, therefore f of 3 will be 9 minus 18a plus 2 minus 2a plus 9a square, right? This leaves you with 9a square. Then you have minus 18 minus 2, which is minus 20a plus 11, right? If you try to break it up, what are you going to get? This is how you're going to break the middle term as minus 9a minus 11a happens to be minus 20a, and when you take the product, you get 99. So over here, take out 9a common, you're left with a minus 1 minus 11, a minus 1. This gives you what? 9a minus 11 and a minus 1. So f of 3 is coming out to be broken up into two distinct factors, 9a minus 11 and a minus 1. If you want f of 3 to be positive, if f of 3 is positive, that means this is positive, right? Product of these two things is positive. How do we basically try to get the range of a for which this product is going to be positive? Well, we go and plot the number line. Infinity, this is minus infinity. What are the two important points which are being denoted over here? A equals 1 and a equals 11 by 9, which is greater than 1. Fine? So this is what you have. Now, if you plug in the values of a which are less than 1, values which are less than 1, that is going to give you what? What is that going to give you? If you plug in the values less than 1, this factor will be negative, Plug in the values less than 1, they will automatically be less than 11 by 9. So this factor is going to give you negative answer. Negative into negative makes it positive. If you plug in values which are greater than 1 but less than 11 by 9 over here, if A belongs to such a range, what is going to happen is plugging in a value which is greater than 1 is going to make this factor deliver you with a positive answer, but this is going to deliver still a negative answer. So positive into negative is negative. And then if you take any value greater than 11 by 9, this is positive, so the product is positive. Right? And therefore we have obtained for which A's on the real line is this factor coming out to be positive. So for A is equal to, or A is belonging to the range of minus infinity to open 1, and A is belonging to the range of 11 by 9 comma infinity. Fine. So from the first condition of discriminant, I have obtained that if I have a quadratic equation whose both roots are strictly greater than 3, that means definitely its discriminant will be non-negative. That means definitely A has to be greater than or equal to 1. If I have an equation, quadratic equation whose both roots are strictly greater than 3, definitely A into f of k would be positive. For A into f of k to be positive, definitely A will be belonging to this range. So I have got A is greater than or equal to 1. I have also got A is belonging to such a range. There is just one more condition left. Let's see what that is. There are 3 conditions which get satisfied if there is a quadratic equation with both its roots to be strictly greater than a constant k. The third condition is that minus b upon 2a would be greater than k. Now what is b? B is minus 6a, so minus b will be 6a upon 2 into a. A is your 1, so you're just left with 2, strictly greater than k, which is your 3, which implies 6a is greater than 6, which implies a is greater than 1. So I have got 3 restrictions on A from the 3 conditions which are true for this quadratic equation, because this quadratic equation which is given to me in the question has both its roots strictly greater than 3. That means this is also true, this is also true, and this is also true. Fine? And that is why, to find out the range in which A lies, why are we doing that? Because I want such an A which satisfies this also, and this also. That means I have to find A which lies in the common region of all 3 these regions. What is that region? Let's find out. So I have, if I talk about the number line, this is my 1 and this is suppose 11 by 9. Fine? First condition says A has to be greater than or equal to 1. So it can be either 1 or greater than 1. 1 is included. Either 1 or greater than 1. This is the range of A's which is coming from the first condition. Second condition says A belongs to minus infinity, comma 1, 1 open, 11 by 9, comma infinity, where 11 by 9 is open. So minus infinity to 1. 1 is excluded, and 11 by 9 again excluded to infinity. So this range and this range is the range given by the next A. Fine? The third A's range we have is A is strictly greater than 1. That means what? I can alternatively write it as A belongs to 1 comma infinity. It's strictly greater than 1. So this is what I have from the third very answer of A. So what is the common region? You can definitely see that this region is the common region. That means those A's for which discriminant will be non-negative, a into f of k will be positive, minus b upon 2a will be greater than k. Which a's are there? The a's are these a's. Therefore, the appropriate range of the unknown a given to me in the question is what? 11 by 9 open, okay, 11 by 9 open, comma, infinity, because it's not included over here. Fine? And that is what is my a for which, these are my a's for which this particular quadratic equation is going to have both its roots greater than the constant 3. Let's see which option gives me that particular answer. 11 comma infinity, no, that's wrong. 11 by 9 comma infinity, yes, that's correct. Minus infinity comma 1 union 11 by 9 comma infinity, no, that is just going to satisfy partially all the three conditions of this particular quadratic equation to have both its roots greater than 3. Fine, this is wrong, even this is wrong. Okay, this happens to be the first way of tackling the questions coming from quadratic equations. Okay, let's move further and see what happens to be our next very question in this league. Here you have alpha and beta to be given as two roots. Read the question carefully. What is given in the question? A quadratic equation is already given to you. Also, you are given something extra about the roots. Take a look. Here alpha and beta, where alpha is less than beta, be the roots of this particular quadratic equation, where c is less than 0 is less than b. That means b is given to be positive, c is given to be negative over here. Then you have to answer among these four very options. Now see, here basically what are they trying to do? If you carefully observe, there is information given to you about roots and there is information given to you about c and b, which are nothing but the coefficients of this quadratic equation. So here they are talking about roots or they are talking about the coefficients. What is that one article which basically triggers us to use the connection between roots and the coefficients? The relationship, what is the relationship between the roots of a quadratic equation and the coefficients of that quadratic equation? We know that, come on. What is that? If ax square plus bx plus c equals 0 has two roots, alpha and beta, then I know sum of the roots. Sum of the roots is alpha plus beta, which is minus b upon a. That's how it's connected to the coefficients. If I talk about product of roots, which is alpha into beta, that is c upon a. Fine? So if this concept is on your fingertips, and let me remind you, over this concept, umpteen number of times questions are being asked in JEE. Umpteen number of times. Just this connection between roots and the coefficients. Okay? So if you are aware about it thoroughly, you will be able to attempt this question like anything, very, very easily. So over here it is saying alpha and beta are the two roots of this very equation. Over here, the only difference between this and the general form of equation is that there is 1 written over here in place of a. And therefore, the sum of the roots will be minus b upon 1 and product of roots will be c upon 1. That's it. So, for x square plus bx plus c equals 0, sum of the roots, alpha and beta are already given to be the names of the two roots of this equation. It will be minus b upon 1 and alpha into beta will be c upon 1. So b and c are very important constants over here. What is the information given about b and c? It's given c is less than 0 is less than b. That means b is positive and c is negative. If b is positive, then minus b is negative, right? And c is already given to be negative. That means sum of the roots is negative quantity, product of the roots is negative quantity. Now see, as alpha into beta is a negative quantity, because alpha into beta is equal to c and c is negative, this implies alpha into beta is less than 0. Fine. Product of two numbers is less than 0 only when one is positive, other is negative, right? So alpha can be positive, beta can be negative, or alpha can be negative, beta can be positive. If alpha is less than 0 and beta is positive, this implies alpha has to be less than beta. Negative number is always less than the positive number. In this case, you can get alpha into beta to be negative, or alpha can be positive, beta can be negative. Fine. In this case, this would imply beta is less than alpha, because beta is a negative quantity, alpha is a positive quantity. This is also going to imply alpha into beta to be negative. So either this is true or this is true. How to find out which is true? It's given in the question. Let's go back. It's given to me that alpha is less than beta. So if among alpha and beta one has to be negative, one has to be positive, definitely alpha has to be negative and beta has to be positive. Because if alpha is positive and beta is negative, beta will be less than alpha, which is going to violate this condition. So alpha has to be negative, beta has to be positive. This condition cannot arise. Fine. So from here we know that alpha is negative and beta is positive. So thus, definitely alpha is negative and beta is positive. So over here just see, if alpha is negative, the fourth option says alpha is positive, right? Beta is positive, the third option says beta is negative. So till here only two options are cancelled by us. Either one is true or two is true. Which one is true? Let's find out from the next condition of sum of the roots. From the first condition of product of the roots, we have found out that alpha is negative, beta is positive. Now imagine, start making your brain work. You have a negative quantity alpha plus a positive quantity beta giving you a negative quantity. Are you understanding? A negative quantity alpha plus a positive quantity beta is giving you a negative quantity. That means what? Something like this is happening. It's almost like a negative quantity alpha plus a positive quantity beta is giving you a negative quantity. That means for alpha plus beta to be negative, this negative quantity alpha has to be numerically greater than this positive quantity beta. Because if this is numerically less than this, for example, this is minus 1 plus 2. Here also alpha is negative to be minus 1, 2, beta is positive. But minus 1 plus 2 is going to give you 1 which is not less than 0. In order to get less than 0, minus 5 plus 2 is giving you less than 0. That means alpha has to be negative, beta has to be positive, plus alpha has to be numerically greater than beta for alpha plus beta to be negative. What do I mean by numerically greater than beta? That means if you take out mod of minus 5, it is 5. Take out mod of 2, it is already positive, so it is 2. So 5 is greater than 2. Until and unless mod of alpha is not greater than mod beta, which is beta only, until and unless mod of alpha is not greater than beta, alpha plus beta is not going to give you a negative quantity. So for alpha plus beta, for alpha plus beta to be negative, alpha has to be numerically greater than beta. Okay? This implies mod alpha has to be greater than mod beta, but mod beta is beta because beta is positive. Fine? So from one condition I have got that alpha is negative, beta is positive. From the second condition I have got that alpha is negative, beta is positive. No. I add on the condition is that numeric value of this negative quantity alpha is greater than the numeric value of the positive quantity beta.